Hey class, I wanted to take a minute to talk about bitwise information, why it's important in computer science and in Python, why we have the concept of bit shifting, bitwise and, bitwise or, bitwise exclusive or, etc. But to understand that, we kind of need to go back in time. Back in the day, we didn't have the hardware, the resources available for programming. And so there was a lot of focus on optimization and keeping things small and using small ideas and optimized ideas to really get computers running and accomplishing what we needed them to do. To understand that, we need to understand a little bit more about bits and what are they. A bit is either a one or a zero. Just like in computer, it's that binary state, one or zero, off or on. And again, just to give you an idea a little bit about size, you have a bit, which is a one or a zero. It's an on or an off state. And then you have 4 bits, which is a nibble, 8 bits, which is 1 byte, 1,000 bytes gets to a kilobyte, 1,000 kilobytes gets to a megabyte, 1,000 megabytes gets to a gigabyte, 1,000 gigabytes gets to a terabyte. Now, honestly, what you'll find is that these are more actually in increments of 1024 because they're bases of 2. However, for the example, I just wanted to show you really how big this data can be when we're talking about gigabytes of stuff, because we're talking about values. And you talk about a character that's in a file, each character is 4 bits. It's represented on a machine in 4 bits in most cases. Sometimes these things can change when you start interacting with embedded systems, etc. But in a standard computer, a letter is 4 bits. And so we start talking about these sizes and about how things line up and storage and really optimizing, because when we write a program, again, if we're going back in time, we want it to take as little space as possible but still accomplish what we need it to. One of those ways that these were used or that this was accomplished is we had 8-bit architectures, excuse me, 8-bit numbers, which represented file permissions in a Unix file system. And again, this existed for a long time, and it still does actually in modern Linux systems and in BSD as well. But again, these systems are broken out where you have a file, and that file is represented in 3 different ways. You have an owner, you have a group, and you have other. But each of those different categories have the ability to read, write, and execute. And so what we found is that we could store those in an 8-bit value. And so when we have these 8-bit values, you have 0 through 7, which represent a numerical value. And any one of these can represent a thing. So in this case, if everyone, the owner, the owner, the group, and everyone else can read, write, and execute a particular file, it would have the value of 777. And so what was really great about this is you could use a number, just one number, one bit, one 8-bit value, which could store all of these different sets of permission. And so this was great because you could read, write, and execute for a particular owner, etc. And it would be so small that you could make things really optimal. And so then to change and modify these, you would shift a bit, modify it. So in this case, if we wanted to create a file, so for this example, my file has the permission of my file read write, has a binary position of 110, which is the same thing as 6. In this particular case, then we would look at this if I printed this out. Actually, let's just go ahead and do this. Print int my file read write. So just to show you that that really is 6. You can see here it's a numerical value of 6. This would mean that I could then read and write. And sometimes, if we're doing a check against something, we don't necessarily want to have to dig into the details, pull the file, look at the settings. What we can do is we can actually look at this permission. And so this is where bit masks come in handy, because we have the ability of using ANDing, or we have ORing, or we have exclusive ORing to be able to set, modify, etc. So in this case, we want to just check, can the person read the file? So I'm going to create this mask, and the read position is the first one, so I'm just representing that here like this, which actually is the number of 4. And if I come down here and I were to say, let's go ahead and erase this, and I just want to say print I can read this file. Oops. And we're going to say if, and we're going to take the bitwise mask here, so if my file read write, and we AND it to the can read mask, is equal to, let's go ahead and put these in parentheses, is equal to the can read mask, then they can read the file. Otherwise, I cannot. Okay, so if I go ahead and run this, what we're going to see is that I can read this file. Because again, with the AND logic, we have if, I'll go ahead and make this like this, AND logic, Boolean AND, or bitwise, sorry, which is one of these. If we have a truth table and we're comparing two things, A and B, then what we'll find is that if A is true and B is true, go ahead and make a little thing here. What we'll find is that this is true, because true and true is true. If we find that A is false, but B is true, the outcome will be false. If A is true and B is false, the outcome will be false. And lastly, if A is false and B is false, the outcome will, of course, be false. Now, if we were to go with the bitwise OR logic, or this pipe symbol, which is the straight vertical line, it's generally on a US keyboard found underneath the backspace with the backslash. What we'll find is that the logic is just a little bit different here. Because again, just like if A or B, then this is true. If A or B, this is true. And then, of course, if false or false is still false. Then we have exclusive OR logic. Or the little caret or hat symbol. What we find is a little bit different again. That true is false, because again, it can't both be true, and it can't both be false. It's only when it is one or the other. And so with these logics, we can kind of come up with different things. In most cases, you'll find that ANDing it is the easiest way to determine whether or not it is true. And so in this case, again, we're coming here and we're evaluating, does this have a number in this position? And in this case it does. And then also, this mask is how we determine that. Because if this were false, again real quick, if I can modify this to 0 and I disable that and say that it does not have that read permission, I cannot read this file. Because again, when I try to AND it, we get one of these scenarios here, where it's one is true, one is false, they line up, and it gets false, which then triggers, this is not true. You can't read it. And so it doesn't match. The value does not remain constant on that particular location. So, with this, we're able to determine what that value is. And so we can do the same thing with any of these positions. If I were to create a can write mask, which is in this case the value of 2, then we would be able to go over these and do the same thing. Let's copy this, paste it down here. We'll just do a little bit of modification here. Can write. I'll go ahead and run this again, and we'll see that I can write to this file while I cannot read it currently. Again, and this just gives us a way to very quickly look at a number and modify or set that value. The other thing that's really nice about it is that you can do mathematics based off of shifts as well. So if I were to have the value of 2, this would be binarily represented as 1, 0. And if I wanted to do 2 times 2, or square this, I could then do 2, shift 1 value, and shift that twice. And so literally what this is doing is this is then saying, okay, I'm going to modify this just a little bit here so it looks like that. In this case, we're then saying, okay, that now looks like this. We'll put another 0 in front of here for the case of below. And at this particular case, we're now at that. Essentially, we've moved that 1 over a position in the binary. So if I print these, and I print them out like this, you will see that the numerical values have been shifted a value. And in this case, I could also have used number 2, because it still would have done the same thing. Because again, we're taking a value in memory and we're doing a bit shift against it. So as you can see, nothing has changed, values are still there. Okay, well what if we want to move the other direction? What if I take number 8 and I shift it, let's do this other number, and I shift it over 3. What is this going to do? Well, let's take a look. Now the value is 1, because we've taken this value, we've moved it 3 times, so 1, 2, 3. Now this value is 1, 2, 3, 1, and that is what we have, which is the value of 1 in binary. So this allows us an opportunity to manipulate, shift, so on back and forth, or apply a mask if we like to interact with numbers, interact with data, and it allows us to take a concept like, say, even file permissions and sort as a number. And that number is much smaller than a big set of variables, etc. And so it allows you to say, this is what it actually represents if I see this number. So again, if I see the number of 7 here, then that's that. If I see the number of 5 here, they can read and execute, but they can't change it. That would be 5. And then on this particular one, if it was 100, they can only read it, but they can't execute it, then this would be a 4. And so with this, Linux and Unix have decided that this is a really great way, because it's so small, to be able to interact and manage information in files, and allows users, groups, etc. to manipulate what this data means. So hopefully this has been helpful. Let me know if there's anything else I can clarify or help you understand about this. Again, the idea is that when you're applying this information, it's checking to see if the number is in the space that we expect it to be. And so when we apply that mask, that's how it works. If you were to do an OR on this, you could do that. But what you would find is that you're not, in this particular case, trying to do that. Maybe in that case, if you were to OR it, you're saying set right value. mask, and that would be 0B010, still the number of 2. And in this case, we would do set file equals my read write permissions currently. We OR that with the 0B010. That would then be able to set that value whether or not it's there. And that would be really nice. So again, this is a particular way that we're able to check to see if things are set, if they're not set. If we have an exclusive OR, that's a way that we can guarantee a particular set of numbers are set, a particular way we can verify that the permissions are set properly. Again, let me know if there's any way that I can help clarify this, make it any easier. Again, it's primarily meant to be focused around a numerical logic based off of binary. Again, you can use hex values, you can use octal, but it's all based around this idea of how am I shifting values. So again, hopefully this has been helpful. Let me know. Thanks.